You know what's strange? Some researchers now believe a new generation of battery designs could reduce the need for some harsh acidic processes commonly linked to older battery manufacturing. And the surprising part is that some materials being discussed are incredibly common. In online conversations, people sometimes compare the cost of certain experimental ingredients to the price of a cheap snack or cup of coffee. No special tools needed to understand the basic idea, no professional required to follow the concept. Just a different way of thinking that suddenly has engineers and automakers paying attention. Before we go further, this content is for educational and informational purposes only. It is not engineering, financial, legal, or technical advice. Battery systems are extremely complex. Manufacturing methods vary across industries, and viewers should always do their own research before trusting claims about emerging energy technologies. Some ideas discussed here are based on historical research, public scientific discussions, and commonly available information. Results in future developments may vary depending on testing, manufacturing quality, and real-world conditions. For more than 100 years, people believed high-performance energy storage had to follow one path: expensive materials, complicated mining, specialized factories, massive industrial systems. Over time, lithium became the center of that world. Phones depended on it, laptops depended on it, electric vehicles depended on it. Then something unexpected happened. Researchers began revisiting older ideas, not fantasy technology, not impossible science fiction, real chemistry that had existed quietly in research papers for decades. And suddenly, people started asking a strange question. What if the future of batteries is not about making everything more complicated? What if it's about simplifying things? That idea changed the conversation. Traditional lithium systems can become extremely expensive when you include mining, transportation, cooling systems, industrial refining, and recycling costs. In some places, replacing a large electric vehicle battery can cost thousands of dollars. Add safety systems and specialized labor, and the expense becomes enormous. Now compare that to what some researchers are exploring today: more abundant materials, reduced dependence on certain toxic compounds, alternative electrolytes, battery concepts that may produce fewer harmful byproducts during manufacturing, potentially lower long-term costs if production improves. That contrast alone gets attention. Because for years, many people assumed powerful energy storage always had to involve major environmental and economic trade-offs. But history tells a more interesting story. Back in the early 20th century, inventors experimented with many different battery chemistries. Some explored nickel and iron, others tested sodium-based systems. Some researchers even worked with semi-solid concepts long before modern electric cars existed. The challenge was not always scientific possibility. Often it was manufacturing limitations or commercial practicality. Lithium eventually dominated because it stored a large amount of energy in a small space. That made it ideal for portable electronics and later electric vehicles. But lithium systems also introduced challenges: heat sensitivity, mining pressure, recycling concerns, dependence on regions rich in critical minerals. Over time, scientists started asking another question. What if future batteries focused less on maximum power and more on balance? Balance between cost and performance, balance between durability and scalability, balance between storage and environmental impact. That shift opened the door to different approaches. Some newer battery concepts use materials far more common than lithium. Sodium is one example. Sodium exists almost everywhere and can be sourced through large industrial processes connected to salt production and other industries. While sodium batteries may not always match lithium energy density, some researchers believe they could become useful for affordable transportation, grid storage, and backup power systems, where low cost matters more than compact size. That's one reason phrases like zero acid and reduced toxic waste started appearing online. But there's an important detail many headlines ignore. No industrial process is completely impact-free. Every battery system still requires manufacturing, transportation, energy, recycling, and material extraction. The real discussion happening inside the industry is whether newer chemistries could reduce some environmental pressures compared to older systems. That distinction matters, because internet hype often turns complicated engineering into dramatic clickbait. What researchers are really studying is whether future systems can become safer, cheaper, easier to recycle, and less dependent on rare materials while still remaining practical. And strangely enough, many of these ideas connect back to research that existed decades ago. One example involves water-based battery concepts. For years, people assumed water and advanced batteries could never work efficiently together because water creates voltage limitations. But improved materials allowed scientists to revisit those assumptions. Suddenly, old concepts that once looked impractical started appearing in modern laboratories again. Another major area involves solid-state batteries. Traditional lithium-ion systems usually rely on liquid electrolytes that help charged particles move between materials. Those liquids can create stability and heat management challenges under certain conditions. Solid-state concepts attempt to replace those liquids with solid materials. Researchers hope this could improve safety and lifespan, although large-scale manufacturing still faces major obstacles. This is why companies around the world continue investing billions into battery research, not because current systems suddenly stopped working, but because industries realized the next breakthrough may come from simplifying chemistry instead of endlessly increasing complexity. Tesla became connected to this conversation because the company helped turn battery technology into a mainstream topic. Suddenly, ordinary people started paying attention to charging cycles, energy density, recycling methods, and supply chains. That shift changed awareness everywhere. Now people hear about sodium-ion cells, they hear discussions about cobalt-free batteries, they see researchers experimenting with sulfur compounds, silicon anodes, and lower toxicity materials. And many are surprised to discover that some of these ideas were explored generations ago. In some ways, modern battery science resembles archaeology. Researchers keep rediscovering concepts that were technically possible decades earlier, but commercially impractical at the time. So how do these systems actually work? At the simplest level, every battery depends on movement. Charged particles move between materials through chemical reactions. As electrons travel through an external circuit, electricity becomes usable power. Different materials influence charging speed, voltage, heat generation, lifespan, and safety. That's why chemistry matters so much. A tiny change inside a battery can completely alter cost, durability, or performance. Lithium became popular partly because it is extremely light. That helped manufacturers build smaller portable devices. But lighter materials are not always the cheapest or most abundant. Sodium is heavier but far more available. Iron is cheap and widely distributed around the world. Every material creates trade-offs. And understanding those trade-offs explains why battery technology keeps evolving instead of settling permanently on one perfect solution. There's also a larger environmental reason this conversation matters. As energy demand increases globally, storage systems become more important. Renewable energy sources like wind and solar do not always generate power consistently throughout the day. Storage systems help balance supply and demand, but building every future storage system around one expensive chemistry may create economic and supply chain pressure. So industries started exploring alternatives, not necessarily replacements for lithium in every application, but additional options. A sodium-based battery might not replace every high-performance electric vehicle tomorrow, but it could potentially power affordable city transportation or stationary backup systems in ways that reduce costs and material pressure. Different technologies for different jobs. That idea fascinates many researchers. The future may not belong to one perfect battery chemistry. It may belong to several chemistries working together depending on the situation. There's also an economic side many people overlook. Battery companies do not only sell batteries, they build entire ecosystems, charging infrastructure, software optimization, recycling networks, manufacturing facilities, supply contracts. That means even small chemistry improvements can influence billions of dollars across transportation and energy markets. Now, if you're wondering why some alternative battery concepts remained overlooked for so long, the answer is surprisingly practical. Manufacturing momentum. Once factories and supply chains become optimized around one chemistry, changing direction becomes expensive and risky. Even promising technologies can remain hidden for years until economics shift enough to justify investment. History is filled with examples like this. Some inventions arrived too early. Others waited for material science to improve. Battery development followed the same pattern. And this leads to one of the biggest misconceptions online. People often imagine innovation as a dramatic overnight invention. But real technological progress usually happens slowly. Small breakthroughs stacked together over time. Better cooling systems, more stable electrodes, smarter charging software, more efficient recycling. Tiny improvements eventually create systems that appear revolutionary from the outside. That may be exactly what's happening now. Researchers around the world are experimenting with battery designs intended to reduce fire risks, improve recyclability, lower material costs, and extend lifespan. Some concepts succeed, others fail. Many remain experimental for years before large-scale adoption becomes realistic. But the overall direction tells an interesting story. The industry increasingly appears interested in abundance, stability, and sustainability rather than only chasing maximum power. Earlier inventors often focused heavily on durability and material availability because industrial resources were limited. In some ways, modern researchers are rediscovering those priorities under different environmental and economic pressures. So if someone wanted to follow these developments responsibly, what should they actually do? Start simple. Read public research summaries instead of relying only on viral headlines. Compare multiple sources. Pay attention to words like prototype, experimental, and under development. Those terms matter. Many exciting battery concepts perform well in laboratories, but still require years of testing before becoming commercially practical. Another useful step is learning the difference between energy density, charging speed, lifespan, and stability. Online conversations often focus on only one category while ignoring the others. For example, a battery with slightly lower energy density could still become valuable if it costs less, lasts longer, and uses more abundant materials. That's why context matters. No battery solves every problem perfectly. Engineering is usually about balance. Still, many people remain excited because these newer concepts suggest something larger than just better gadgets. They hint at the possibility that future energy systems could become more diversified and potentially easier to manage environmentally over time. Not instantly, not magically, but gradually. And perhaps that is the real hidden story behind all of this. Sometimes industries spend decades pursuing maximum performance while overlooking simpler alternatives that later become valuable under different conditions. History repeats that pattern constantly. Old ideas disappear, technology improves, economic pressure changes, then forgotten concepts suddenly return looking revolutionary. Before we finish, remember that this content is only for educational and informational purposes. It should not be treated as engineering, investment, environmental, or technical advice. Battery technologies involve complex manufacturing systems, safety considerations, and scientific limitations. Anyone exploring these topics should review multiple reliable sources, use caution, and test information carefully before drawing conclusions from online discussions or demonstrations. And honestly, that may be the biggest lesson hidden inside this conversation. The future is not always invented from scratch. Sometimes it begins when people revisit old ideas using better tools, improved materials, and a different perspective. If this helped you understand something new about batteries, energy storage, and the future of technology, share it with someone who enjoys learning about science and innovation. And subscribe for more educational content exploring forgotten ideas, overlooked history, and the technologies quietly shaping the world around us.